Theorem on dynamical system. First theorem: if A is non-singular matrix, then the eigenvalues of A inverse are the reciprocals of the eigenvalues of A, matrix A. So this is what we want to prove here. So for example, if we consider an example, say for consider a matrix A is equal to 7 minus 5. Consider matrix A is equal to 7 minus 5, 4 minus 2 minus 2. Then the first, if we find its characteristic equation, then we get lambda square minus trace of A into lambda plus determinant of A. First of all, we are going to check whether it is a non-singular. So determinant of A is equal to minus 14 plus 20, which is equal to 6, not equal to 0, and therefore it is what? Non-singular matrix. So determinant of A is equal to 0. Now when this theorem is applicable, if it is a non-singular, so it is lambda square minus trace of A. So what is trace? 7 plus minus 2 into lambda plus determinant of A, which is equal to 6. So what is the trace here? The trace is the addition of diagonal entries is trace. So 7 minus 2, this is what? The trace of matrix A. So now next, this implies this is equal to lambda square minus 5 lambda plus 6 is equal to 0. So here it is lambda minus 2. The roots of this quadratic equation is lambda minus 2, lambda minus 3 equal to 0, and this implies the eigenvalues are lambda 1 is equal to 2 and lambda 2 is equal to 3. So these are the two eigenvalues. Next, we want to show that the eigenvalues of A inverse is 1 by 2 and 1 by 3. So what is given here in the next step here? Now since A is equal to 7 minus 5 and 4 minus 2, then A inverse is equal to now if A is equal to A, B, C, D is the given matrix, then A inverse is equal to 1 by determinant of A into diagonal entries. We change here diagonal entries, that is D, A, and we change the sign here, minus B minus C. So this is what A inverse of the given matrix. We interchange the diagonal entries, and for non-diagonal entries we interchange the sign. So here the A inverse is equal to minus 2, 7, and interchange the sign. So 5 minus 4 and divide by determinant of A. So what is determinant of A? It is 1 by 6. So this is the matrix that is here. It is equal to A inverse is equal to minus 2 by 6, 5 by 6, minus 4 by 6, and 7 by 6. So its characteristic equation is equal to, characteristic equation is again lambda square minus trace of A. So minus 2 plus 5, so it is equal to 5 by 6 lambda. And what is determinant here? Minus 2 by 6, 7, minus 2 into 7, this is equal to minus 14 plus 20. So this is equal to 6 by 6. So this is nothing but it is equal to 1 equal to 0. So if we simplify this, it is equal to what is determinant here? Minus 2 into 7, it is minus 14 by 36. This is what? 36. And here it is 20 by 36. So this is 6 by 6. It is 1 by 6. So if we simplify this, this is equal to 6 lambda square minus 5 lambda plus 1 is equal to 0. If we multiply 6 on both sides, we get 6 lambda square minus 5 lambda plus 1 equal to 0. So again we want to determine here two number whose product is 6 and addition is minus 5. So it is 6 lambda square minus 3 lambda plus 2 lambda plus 1 is equal to 0. Now if we simplify this, so this is equal to, if we take 3 lambda outside, it is 2 lambda what is 2 lambda minus sorry, here minus sign, not plus, here is a minus sign. So 2 lambda minus 1, and if we take minus sign outside, it is 2 lambda minus 1 equal to 0. So if we take 2 lambda minus 1 outside, it is equal to, inside the bracket, 3 lambda minus 1. So this implies 2 lambda minus 1 equal to 0, or 3 lambda minus 1 equal to 0. So this implies lambda is equal to 1 by 2, or lambda is equal to 1 by 3. So you can verify here, if A is the given matrix, here A is the given matrix, its eigenvalues are lambda is equal to 2, lambda 1 is 2 and lambda 2 is 3, and next we find its determinant. This is the determinant of matrix A, and we find its characteristic equation. This is what the characteristic equation of A inverse, characteristic equation of A inverse. And therefore and if we solve this quadratic equation, we get eigenvalues is 1 by 2 and 1 by 3, and therefore if eigenvalues of A are 2, 3, then eigenvalue of A inverse is 1 by 2, 1 by 3. So same here, we want to prove here. So what is given? Now to prove this theorem, the given part is, given A is non-singular matrix. Now what is meant by we are going to discuss it further. So A is non-singular and is non-singular matrix, and this is a given. And then what is our claim? Our claim is the eigenvalues of A inverse, eigenvalues of A inverse are the reciprocals of the eigenvalues of matrix A. So given A is a non-singular matrix, and and our claim is eigenvalues of A inverse are the reciprocals of eigenvalues of A. So prove this. Let lambda be an eigenvalue, value of A with corresponding eigenvector vector x. So by definition of eigenvalue, we can write this as, this implies Ax is equal to lambda x. Say this is equation number star. Okay, but now given, since A is non-singular, this implies determinant of A is not equal to 0, and this implies A inverse exists, and it is a square matrix, so A inverse exists. So if you multiply A inverse to both side of equation star. So we want to multiply this equation star A inverse, so we get A inverse into Ax is equal to A inverse into lambda x. But we can write this as A inverse A into x is equal to Now since lambda is a constant value, take it outside the this matrix multiplication or vector multiplication. So this is equal to what? A inverse x. But what is A inverse into A? It is equal to identity matrix is equal to lambda A inverse x. So this implies, but what is identity matrix I into x? It is equal to x. Since it is an identity matrix, so this is x is equal to lambda A inverse x. Now this implies if we divide lambda to this side, we get 1 by lambda x is equal to A inverse x. So in other words, this equation can be written as A inverse x is equal to 1 upon lambda x, and therefore what is the eigenvalue here? What is lambda? Lambda is the eigenvalue of A. Here you can check, lambda is an eigenvalue of matrix A. Then what we get here? We get A inverse x is equal to 1 upon lambda x. This implies 1 upon lambda is an eigenvalues of matrix A inverse. That is, it is what? Reciprocals of lambda. So this is the definition of eigenvalue. If lambda is an eigenvalue with corresponding eigenvector x, then we get x is equal to lambda x. So if x is equal to lambda x, implies lambda is eigenvalue. This lambda is what? Eigenvalue. Similarly here we get A inverse x is equal to 1 upon lambda into x. Therefore 1 upon lambda, here eigenvector remains same, x. Okay, but what is here? Eigenvalues we get reciprocals, and therefore and hence we get from this we can write the eigenvalues of A inverse are eigenvalues of A inverse are reciprocals of matrix A, reciprocals of the eigenvalue of matrix A, hence the proof.